Now we are going to study the chapter 6, Electricity and Magnetism, and in this lecture we will discuss the basic concepts of electricity. Let's talk about the Benjamin Franklin. He is well known as a statesman, but he also was an important scientist who studied the nature of electric charge and introduced the terms of positive and negative to describe charges. The subatomic particles are electrons, protons, and neutrons. And there are two kinds of electric charges in an atom, the positive and the negative charges. The electrons have a negative charge, and the protons, which are in the nucleus, have a positive charge. Then the electrons have a negative electrical charge and protons have a positive electrical charge. When the electrical charges interact, they create an electrical force. If the charges are like, for example, if both charges are positive, then they produce repulsive force. If the charges are unlike, means if one is positive and the other is negative, then they produce attractive force. Electricity is another form of energy resulting from the existence of electrons and protons. The electricity can be statically as accumulation of charge or dynamically as a current. Then let's first explain statically electricity. We know the electrons can move from one object to another by friction. For example, when we rub two objects or when we rub our hands. But what happened before rubbing the objects? They are neutrally charged, means they had the same number of protons and the same number of electrons. In this example, we had a neutral lithium atom. We can see we had 1, 2, 3 electrons and we had 1, 2, 3 protons. Means this atom is neutral. This atom has the same number of positive and negative charges. But in some cases, because of frictions, the objects can be positive or negative charges. If the object loses electrons, then result in a positive charged object, like we had in this example. If the object gains electrons, then result in a negative charged object. Then we can define the electrostatic charge as an excess or deficiency of electrons. And also we can define static electricity as imbalance of electric charge within the material or on the surface of the material. And the charge will remain in that object until it will be able to move away. How the charge can move away? By electric current or by electric discharge. This is why when our body is charged and we tap the door knob, we feel that sad because our body is discharged. There are three ways to transfer charge. One is by friction, the other one is by induction and by contact. Friction occurs when there is a transfer of electrons from one object to another object. Induction occurs when there is the redistribution of charges in a material. And contact when there is a direct contact with a charged body, which results in a transfer of electrons. One example of charge by friction occur when we comb our hair. What happens before we comb our hair? then the hair is neutrally charged and the comb also is neutrally charged. We can see the net charge equals to 0, same number of positive and negative charges. Now, what happened after we comb our hair? Then we can see the hair lose electrons, and now the hair is positive charged. In case of the comb gain electrons, and now the comb is positively charged. Then now here is the net charge is positive, and the net charge in case of the comb is negative. And this is why when we move the comb close to our hair, we see the hair is attracted by the comb, because we know positive and negative charges they attract. We had one more example of transfer charge. In this case, there is a person that is rubbing a plastic tube using a piece of fabric. During this process occur a transfer of charges between these two objects. After that process, the tube is charged negatively because the tube gained electrons. In case of the piece of fabric, it is positively charged because it loses electrons. If that person brings the tube close of the piece of paper, because the tube is negative charged, that induces a redistribution in the charges of the paper, and this is why all the positive charges in each piece of paper are moving closer to the tube, because the plastic tube is negative charges attract the positive charges, and this is why the paper is attracted by the tube. Then in this example, we discuss the transfer of charge by friction and transfer of charge by induction. In this video, which is a short video, we will show one more example of the charge by induction, and this occurs in the electroscope. Then let's watch the video.
Is the electroscope. These devices were originally designed to detect and measure static charges. This one has two pieces of aluminum foil hanging down from wires attached to a bolt, comes up through the center, and has a large metal ball sitting on top of it. Let's try with a negative charge. Once again, we have a polarization of the electrons away from that negative charge. Now let's try with a positive charge. In this case, the electrons of the metal move towards the positively charged glass.
Now let's define some quantities that we need to know when we are studying electricity. And first is the fundamental charge. The fundamental charge is the electrical charge of one electron, and the magnitude of the charge is 1.602 10 to the power minus 19 coulomb. Then coulomb corresponds to the unit of the charge. If we want to calculate the charge of any object or any material, then we need to multiply the number of electrons by the fundamental charge, means by this value. When there is a positive and negative charges, they create an electrical force. This force is direct proportionally to the product of the electrical charges, but is inversely proportionally to the square of the distance. And we can see that if we use the line test. Yes. More charge, more force, but more distance, less force. And also, we can see this equation is similar to the gravitational force equation. As we had G value is a constant. In this case, the constant is K. Yes. And the value is 9.0010 to the power 9 Newton meter square per coulomb square. Then we had the product of the masses. And in this case, we had the product of the charges. And the force is inversely proportional to the square of the distance in both cases. And you can see they are really very similar. In the next video, I want to show that the force is directly proportional to the charges, but inversely proportional to the square of the distance. More charge, more force, less distance, more force. And let's see the video. Let's watch the video.
Now, wood is actually a very good insulator. In this case, I have an 8-foot 2x4 hanging from the ceiling. And the charge on it is neutral, but we're going to see if we can move it with a static charge. Now we'll get a nice charge on our PVC pipe here and see if we can move it. Okay, there it goes. See if I can reverse directions. With induction charging, I don't have to touch the pipe to the wood. I just have to bring it near it.
In this video, we observe if more charges are transferred to the plastic tube, it is possible to move not only pieces of paper by a plant. Also, we observe that the plastic tube must be closer to the plant because less distance, more force. Now let's solve one problem in which we need to apply the equation of electric force. In this case, we had one rubber balloon with a negative charge of 3.0010 to the power minus 14 coulomb and is suspended by a string and hangs 0.0200 meters from a second rubber balloon with a negative charge of 2.0010 to the power minus 12 coulomb. Then the first question we need to answer is, what is the direction of the force between the balloons? Because both charges are negative, then we know if we have negative forces, they repel because we have like charges in this case. If we have like charges, then they will repel. And this is why this is the diagram that represents this situation. This is why the vectors of the force are in opposite direction, because the force is repulsive force. Now, the second question is, what is the magnitude of the force? To calculate the magnitude, we need to apply the equation. In this equation, we know K is a constant value, is 9.0010 to the power 9 newtons meter square over coulomb square, is the constant in SI system. Q1 and Q2 are the charges, and D is the distance between the charges. And let's write the information we know, and then we can calculate the force. And we know Q1 equals to 3.00 10 to the power minus 14 coulomb. The second charge is 2.00 10 to the power minus 12 coulomb. The distance between the charges, and we will select the meters units because the constant is also meters in the constant of proportionality. Then here meters, let's write here the K value will be 9.00. It will be easier to solve the problem if you write the distance in scientific notation. Then let's write the distance in scientific notation. Because it's a small number, less than 1, we know the exponent must be negative. And we had 1, 2, then will be 2.00 10 to the power minus 2 meters. 3 significant digits in standard notation, 3 significant digits in scientific notation. Now we had all the information. Let's now calculate the force. And the force equals to K value, but K value is 9.00 10 to the power 9 Newton times the first charge, then will be 3.00 10 to the power minus 14 coulomb times the second charge will be 2.00 10 to the power minus 12 coulomb. Divide by the distance, but we need to square the distance. 2.00 10 to the power minus 2 meters. And we need to square the distance. And it's important, don't forget to square the distance. And I will solve the problem step by step. In this way you will see also what happened with the units. And let's multiply first the charges. We have here multiplication. Let's multiply these two numbers together first. Newton meter square over, and 3 times 2 will be 6.00, and we had negative 14 and negative 12. We need, because we are multiplying the bases of 10, then we need to add the numbers. Negative 14 minus 12 will be minus 26. Column times column will be column square. And we can also square this number. We can square the first number. 2 to the second power will be 4. To square the power of 10, we multiply 10. And negative 2 times 2 will be negative 4. And we square the unit also. If you want, you can use also your calculator to solve the problem. You can use your calculator to multiply the numbers, and it's right. And let's see what happened with this units. This to cancel out, this cancel out with this meter square, and the answer is in newtons. This is with the unit we expected because we are trying to find a force. And let's now multiply the numbers together in the numerator. 9 times 6 will be 54, because we have 3 significant digits, then 54.0. 10. 9 minus 26 will be negative 17 newtons. And then now we had 4.00 10 to the power minus 4 newtons. Sorry, not newtons, we already write newtons. No units in this case, because we had newtons on top, is a force. And now we can just divide the numbers. 54 divided by 4 will be 13.5. And now negative 17 minus minus 4. Remember, if we had division, we subtract the exponent in the denominator from the exponent in the numerator. Then you will have minus 17 minus minus 4, which will be positive at the end. Yes, minus 17 minus minus 4, and finally will be positive. Finally, we will have minus 17 plus 4. Then here, let me write here newtons. Then finally, the force will be 0.5 10 to the power. This is a 17. Let me write clearly. This is 17. 17 plus 4 will be negative 13. If you want, also you can write this in number in scientific notation. Then we move one plate to the left, and we know if we move to the left, we need to add 1. Then the final answer will be 1.35 10 to the power minus 12 newton. Let me write here also newtons. And this is the answer. Let me write this one better. And the force, the magnitude of the force between these two balloons is 1.35 10 to the power minus 12 newton. Now we are going to study the concept of electric field. Electric field is related to the space around the electric charge. What happens when there is an electric charge? The condition of space around an object, it changes by the presence of an electrical charge. In this picture, we illustrate the electrical field lines for an isolated charges. In this case, we had a positive charge, and we can see the electric field lines are straight lines and point away from the charge if the charge is positive. If the charge is negative, we can see the arrows of the electric field lines will point towards to the charge. When there is more than one charge in the regions, like in the examples we had here in these diagrams, the electric field lines will not be straight lines. They will curve in response to the different charges. For example, if we had positive and negative charges, the charges they will attract, and this is why the arrows point from the positive charge to the negative charge. In case of the like charge, we know they will repel, and this is why there is no connections between lines when we represent the electric field. In this video, we will see how the Van der Graaf generator shows how the space around the charge change.
The Van der Graaf generator is a must-have when teaching electrostatics and the electric field. For example, you can use it to show that the electric field is higher near pointy edges than rounder ones. You see, it is the electric field that ionizes the air and makes lightning. A pointy edge can do that easier because the electric field is higher. Notice also that these lightning rods are connected to the ground. Of course, you can also use the Van de Graaff generator to demonstrate radial electric field lines. For example, you can tape streamers on the top of the Van de Graaff and they will point radially outward. Or you can use a human. Find a long-haired human and have her stand on a milk crate for insulation. Remove all metal such as rings and glasses and zippers, and with any luck and dry weather, her hair will stand up. Another way to demonstrate electric fields with the Van de Graaff is to hang a string over the charged dome like you're going fishing. Watch as the charged string is amusingly repelled by the electric force field. But I think the most convincing way to show the electric field is with a straw cut in half and pinned to a meter stick.
In this video, we observe how the hollow metal glove that is charged can change the space around it. In other words, we saw the effect of its electric field. Now we are going to define different quantities that we need to know if we are going to study electricity. One of these quantities is the electrical potential of voltage. We know an electrical charge has an electrical field that surrounds it. And what is the electrical potential? Electrical potential is how much work we need to do to move a second charge into the field of the first charge. And this is why the voltage or the electrical potential is defined as work over charge. Now let's see the units. Because we had on top work, as in the numerator work, this is why on top we had joules. In the denominators we had charge, and this is we had coulomb. Then voltage is defined as joule over coulomb. But joule over coulomb has a special name, which is volt. In this picture we had a simple electric circuit which has a voltage source, such as a generator or battery. That voltage source maintains the electrical potential. We had also some device, for example, it can be a lamp, motor, where work is done. And also we had a continuous pathways for the current to flow. Usually they are wires. Then now we can define the electric current. The electric current is usually represented by the letter I and is defined as the flow of electric charge. Means is what is the amount of charge per unit time that pass through a cross-sectional area of a conductor. Means is how much charge per unit time pass for some wires, for example. Then this is why we can define the electric current as electric charge divided by the time. Now let's see the units. Then because we had electric charge in the numerator, then we had coulombs in the numerator. Because we had time in the denominator, we had seconds in the denominator if we are using the units of SI system. Then the current is how much charge per unit time. It is coulombs, the units will be coulombs per seconds. And this unit has a special name, which is amp or ampere, and is represented by the letter A. The materials can be classified as electrical conductors or insulators. Then conductors are materials that can move electrons easily. Good conductors include metals, for example. But insulators are materials that don't move electrons easily. Then they are known as non-conductors or insulators. Then that materials, example of insulators material are wood, plastic, or paper. Let's try to solve this problem in which we need to apply the concept of current. An electric current through a wire is 6 coulombs every 2 seconds. Then what is the magnitude of the current? And because it's 6 coulomb, we know coulomb are the units for charge. Then the charge will be, in this case, 6 coulomb. Every 2 seconds, then these are units for time, then time is 2 seconds. Then we want to calculate what is the magnitude of the current. The current will be the charge per time. Then now we will have 6.00 coulomb divided by 2.00 seconds. And if we divide these two numbers, we will have 3.00 coulombs per second. Means in this case will be flowed 3 coulombs per second. Yes, is the rate of the charge. How much charge per unit time. But also we can write this one like 3.00 amp. Another concept related to the electricity is the electrical resistance or resistance. Well, the electrical resistance is the opposition to movement of electron. This is why if we apply a voltage to a material and we get high current, we say the resistance of the material is small. And vice versa, if we get low current, then the resistance of the material is large. This is why we can define the electrical resistance as the ratio between the potential difference of voltage between 2 points and the resulting current. And this is why we can define the resistance as the ratio between voltage and current. And we can rewrite this equation. We had resistance equals to voltage over current. If we multiply by current on both sides, then this cancel out and we can write this one like this is the equation we had here. Then this equation in this way is correspond to the Ohm's law. Ohm's law is the relationship between voltage, current, and resistance. And also we can rewrite this equation in this way. Yes, it's the same thing, just we change the order of the quantities. And if we plot voltage versus current, yes, if we plot voltage versus current, and we got a straight line, then in this case, the resistance will be a constant value and the resistance corresponds to the slope. And in the final exam, I will give a table with voltage and current values, and then you will have to find the resistance that corresponds to this voltage and current values. And how you will calculate the resistance? You have to calculate the slope of the line. One more thing is the units of the resistance. And because resistance is defined as voltage divided by the current, then we had voltage on top, the units will be volt, and we had current in the denominator, then the units are ampere. Then we will have volts over ampere. And this unit has a special name, which is ohm, and the symbol is the omega letter in the Greek alphabet. Then the resistance, the units of the resistance is volt over ampere, which correspond to ohm. Now let's apply the equation that correlate resistance, voltage, and current to solve these two problems. In the first problem, we want to know what is the resistance of a circuit with 120 volts and 4 ampere. Then in the first problem, we want to know what is the resistance if the voltage is and by the units this 4 amp, then we know this corresponds to the current. Then this is 4.00 amp. Then we can apply the first equation. The resistance equals to voltage over current, and resistance equal to voltage, which is 100 volts divided by 4.00 amp. And the resistance equals 120 divided by 4 will be 30.0, 3 significant digits, and voltage divided by amp, we know this corresponds to ohm. This is the units for resistance. And the answer is the resistance equals to 30 ohms. Then now let's try to solve the second problem. In the second problem, we need to find what is the current. Then we need to find the current in a 60 ohm resistor, and we know this corresponds to the resistance is 60 when the potential difference across it is 120 volts. Then this is the voltage, is 120 volts. Then we can use either the first equation or the second equation. We know they are the same. It's just we wrote the equation in different way. And let's use the second one. And we need to solve for the current. Then we divide by the resistance by R on both sides. Then we have the current equals. And now let's calculate the current. Will be voltage will be 120 volts over 60 ohm. But we know ohm is voltage over amp. Yes, remember ohm, which is the unit of resistance, is voltage over amp. And we can write here the units for, let's write ohm first, and then we will write again this one. Then will be 120.0 voltage divided by 60. Then ohm corresponds to voltage over amp. And let's solve this one. Then 120 divided by 60 will be 2.00. And let's see what happened with the units. Then we had voltage, and now we had to flip the unit. That's because it's divided. We are dividing, then we had to flip the unit, change the division by multiplication, and flip the fraction. And we had here voltage. Voltage cancel out, and finally the current will be 2.00 amp. This is the unit we expected, yes, and it's 2.00 amp. Now let's define electrical power and electrical work. We already mentioned that any simple circuit has three parts: a voltage source that can be a battery, an electrical device in which the work is done that can be a bulb, and conducting wires. We want to calculate the electrical power developed by the voltage source. We know the power is defined as how much work can do in the unit time. This is the work per unit time. Then we know also the voltage can be defined as how much work is needed to move the charge in the electric field of the other charge. Yes? This is the definition of voltage. Then we know what voltage equals to work per charge, and we can multiply on both sides by charge. This cancel out and we will get this equation, and work equals to charge per voltage, and this is the electrical work. Yes, we can calculate the electrical work if we multiply the charge per voltage. Now let's define electrical power. And we know power is work per unit time, but work equals to charge per voltage. Then let's replace this value, this equation, into the power equation. And work equals to charge per voltage per unit time. Then we replace work by this one. Then now we can rewrite this equation. Yes, we had charge per voltage over time, but we can rewrite this equation times voltage. Yes, charge per voltage per divided by time. But we know charge per unit time corresponds to current. Yes, this corresponds to current. And we can define the electrical power as the multiplication of the current times voltage. Then how we will calculate the electrical power? We need to multiply the current times voltage. Now let's see the units. And we know the current is how much charge per time, yes, per unit time. And this is why the units for current is coulomb per second. Yes, we had here the units for current. We know the units for voltage is work over charge. Yes, this is work is joules over charge. And this is what we had here. And what happened is these two units cancel out, the coulomb cancel out, this unit cancel out with this one. And finally, we had joules per second. And we know joules per second correspond to watt. And this is the unit we expected for power. And again, the electrical power equals to the current time voltage. And the units for electrical power is the same units in the SI system, is the same units for the mechanical power, which is watts. Now let's try to solve these two problems applying what we learned. Yes. Then in the first problem, we had an electrical motor draws a current of 14 ampere in a 240 voltage circuit. Then what is the power of this motor in watts? And let's solve the first problem here. Then we know the current is 14 ampere. The voltage is 240 volts. And then we need to calculate the power. And we know the power equals to current multiplied by the voltage. Then current will be 14 ampere. Let me write here the units. Then voltage will be 240 volts. We need to give the answer in watts. Then we know power equals to 40, but ampere is how much current per time, sorry, how much charge per time. Then voltage, but voltage is how much work means it's joules per coulomb per charge. And we know these two units cancel out, and then we can calculate the power. The power equals to 3,360 watts. Because we had here two significant digits, and let's y will be 300. Let me write here the voltage. 3,400 watts. And this will be the power of this motor, will be 3,400 watts. Now let's try to solve the second problem. For the second problem, a light bulb with a resistance of 10 ohms. Let's write here the resistance of 10 ohms allows a 1.20 ampere. Then the current will be 1.20 ampere to flow when connected to a battery. Then we want to know what is the voltage of the battery, and we want to know what is the power of the light bulb. Then let's see what is the voltage of the battery. Then we know voltage current times the resistance, as this is the Ohm's law. And let's now multiply this one. Will be current will be 1.20 amp multiplied by the resistance, which is 10.0 amp. And let's see the units. Then we had 1.2 amp. Let's write here 1.2 amp, 10 amp. But we know ohm is voltage over ampere. Yes, this is the definition of ohm. And these two cancel out, and we had the answer in volt, that this is the unit we expect. Then this is the A. Then the voltage will be 12.0 volts. Let's now solve the second part. What is the power of the light bulb? And the power will be the current multiplied by the voltage. Then current, we know the current is 1 ampere, and the voltage is 12.0 volt. And let's see the units. This is the power. Then in case of the ampere, we know is how much charge per second. In case of the voltage is how much work per charge. This cancel out, you have joules per second, which is watts. Then 1.20 times 12.0 will be 14.4 joules per second. And finally, we had the power is 14.4 watts. And this is the answer. And I am doing with all the steps because I want to make sure you understand that you can skip some of the steps. Yes, you can skip some of the steps when you are solving the problem. Usually the units that appear in our electricity bills are kilowatts per hour. This is how much energy we consume. Yes, it's kilowatts per hour. And what I want to show you is this unit corresponds to units of energy. And usually this is the unit appear in the electricity bill. And let's write this. Then we know kilo correspond to 1,000. And let me write here 1,000. We know watts correspond to how much work per unit time, means joules per second, the units. And also we know in 1 hour we have 3,600 seconds. Then we can multiply here by 3,600 seconds. And we can see these two units cancel out, seconds cancel out, and finally we had the answer in joules. And if we multiply these numbers together, we will have 3,600,000 joules. This is 0. Let me write 0. We can write this in scientific notation, then 1, 2, 3, 4, 5, 6. And this corresponds to 3.6 to the power 6 joules. Now we can write that 1 kilowatts per hour equals to 3.6 to the power 6 joules. And this is the equivalent between the kilowatts per hour and the joules. And we can see is big number. Yes, it's big number. In the table 6.2 of your textbook, you will find the summary of all electrical quantities and its units. And you will see here the quantity, the definitions, and the units that correspond for each quantity. This is all I had to discuss for today.